For the kind invitation. I'm really sorry I cannot participate. It would have been fantastic, but anyway, I'm glad to be part of this meeting. Very interesting. I will talk about work that I've been doing here mainly with my student and with colleagues about thinking of quantum field theory using topological sigma models. Okay? So the aim is to try to reproduce as much as we can results from quantum field theory using a completely different, or if you want to use the word dual, it's fine with action, okay? Which is the property of doing a topological sigma model. So this is work done with here Philippe Diaz, my student, but also with Thomas and Nicolas, Thomas Vasile and Nicolas Boulanger, David de Philippe and Carl Riazola, and Ergin Seskin. So I'm joining here material from various collaborations. I should have put also maybe my old collaborator Johan Engqvist here. Some of the ideas we had are resurfacing. Okay. So the basic idea is that we formulate partial differential equations as Cartan into systems of differential forms, or alias unfolded dynamics of Misha Vasiliev. Okay. So the idea is to write differential equations using differential forms, where the only quote-unquote kinetic term or differential operator is the Gram differential, and then we have nonlinear couplings. That's the first step. So this is still a classical field theory, but such equations arise naturally when you apply variation principle to topological sigma models of AKZ type. I should maybe have written here. And the key feature then is that in order for if the original PDE describes what we usually call a local degree of freedom, say waves propagating in space-time or particles, then these sigma models must necessarily have infinite dimensional target spaces. In particular, there will be infinitely many zero forms. Okay, these zero forms, they provide the integration constants that one can convert to iteration and annihilation operators in the original expansion of the field up here. So, for example, if you expand a scalar field in iteration and annihilation operators, clearly there are infinitely many Fourier coefficients, and those Fourier coefficients appear as a special coordinatization of the target space of this topological sigma model. So these are not ordinary, for example, like Chern-Simon theory with a finite number of connections. It's an infinite dimensional target space. It looks a little bit more like string field theory, maybe, okay, in that sense. We have infinitely many variables to play with. So infinitely many topological fields, each topological field contributing a finite number of degrees of freedom can then sum up to an infinite number of degrees of freedom. Okay. So I stress again that these models can be thought, we use them sometimes in the first quantized context, but it's exactly the same sigma model in the second quantized context. The only difference is whether the target space is finite dimensional or not. And the infinite dimensionality in the second quantized context is not that bad. It simply comes from working with something called horizontal forms. Okay, so you have some fibered space, have a base manifold where the forms live and are valued in functions on the fiber. Okay, so when you expand, you have infinitely many functions in the fiber space, and there comes the infinite dimensionality of the target space. So it's all under, in some sense, control. Okay, yeah. Good. And then finally, so when we plug these, when we quantize these actions, then clearly the expansion coefficients of these topological fields, the homological elements, monodromies, and other classical moduli, they become quantized, become operators. So we get operator algebras attached to defects on the source manifold where we put these sigma models. So I'm putting something in here. So these Cartan integrable systems up here at the classical level, clearly there is no real constraint on the dimensionality. We can think of an unfolded system on some manifold, something called the integrable manifold. So for example, if you take ordinary gravity, let's say, we rewrite it as a Cartan integral system, there's no need for the frame field to be invertible anymore, and we can think of gravity in 0 dimensions, 4 dimensions, or high dimensions. So in this universal manifold, we can imagine different submanifolds. I will use the word defect here for such a pullback or such a restriction of the system to a submanifold. And once we choose such a submanifold, we have a classical moduli space, or to be precise, a 3 differential algebra living on that defect. And that algebra, which is classical up here, we then quantize using an AKZ sigma model. So here it is, we're trying to understand this, but it seems that you can, of course, have defects of different dimensions. And what you do is that then you can attach the defect as a boundary of a one high dimensional source manifold for the AKZ sigma models. And in effect, just some overall possible such extensions. If it is confusing, it is because I am confused about this. We are trying to do our best here. So what we're doing, for example, is that to quantize, say, ordinary massless field, there's no need to make, you can think of just simply a line, a Verl line sitting inside ADS, for example, single circle, okay, time. And the whole space we can throw away is anyway represented through the integration constants inside the target space of the theory. And as we will see here, okay, so the key model which exhibits all this is the original Poisson sigma model, the one of Michela Schaller-Strobel. It has been gauged, okay? So we gauge the sigma model, but we also extended the T star G, okay? So what I mean by that, so the sigma model, they will be symplectic, by the way. So on a symplectic manifold, Poisson-friendly vector fields are all acting with Hamiltonians, okay? The Hamiltonians generate a group, and we add the group to the target space of the sigma model. So the sigma model target space is the original symplectic manifold, direct product T star of a group, okay, where G acts on the manifold. And again, so this is a general model. It can be used again in the first quantized context, which I will do first here, part 1. And we can use exactly the same idea in the second quantized context. Okay. So that means that when we apply, when we think, for example, of Vasiljev's theory of higher spins as a 2-dimensional sigma model, that 2-dimensional source manifold of the sigma model has nothing to do with space-time. Space-time is now sitting inside the target space, inside that G. Okay. So what's going on here is that, well, if you have a 2-dimensional sigma model on the disk, let's say, the boundary is a circle. The circle is, let's say, a Verl line, okay, along these quantum states are moving. So you have an in state and an out state. And that state lives in an operator algebra generated from the coordinates of the target space of the theory coming from the bi-zero form module. Okay. So as far as, if you think functorially speaking, in quantum field theory, we have an S matrix. There are in states and out states and an S matrix mapping them between each other. To describe that, you only need an interval, right? You need, time is tau, let's say, initial and final point and an interval between them. That's all the topology needed to describe an evolution operator. So clearly going higher in dimension in this AKZ context means that we're doing more complicated functorial structures, okay? I'm not even gonna go there. I'm trying to learn this, but we are trying to, instead I will focus on this key model here. This is a 2-dimensional, I should have written maybe also. In fact, the model as it's written can be formulated in 2 or 4 or 6 in any even dimension, but for practical purposes, I will put in 2 dimensions. Good. So I will start by discussing a little bit about quantum mechanics, okay? Just ordinary quantum mechanics, and how to write first quantized higher spin gravity, starting from quantum mechanics, and how to extend these quantum mechanical systems into what we can call quote-unquote tensionless strings. Okay? And here I will make contact with the recent work of Gabriel and Gopal Kumar in particular. And then I will move on to what we call quantum field theory, or second quantized higher spin gravity, and these holographic duals. So I'd like to stress again that what we're trying to do here is to have a single way of thinking, okay? Where this first or second quantized. Hello, yes?
Yes, sorry to bother you. There is some strange noise with the microphone. Is it the one of your laptop or?
Is the noise strange now?
No, now it's perfect.
I don't know. Maybe is it this?
Just be closer to microphone, no?
I will also change my chair because my office chair is very squeaky, but I like it. So I will change it.
Just
my
earphones.
dining is gonna squeak, I think. I think that was maybe the problem actually. Good. Now I have to adjust the angle also. Good. So, so when I say quantum mechanics or QFT, the sigma models will be, at the quick look at them at least, the same. It's just that the target spaces will be different. Okay, here I have a finite dimensional symplectic manifold. Here I have an infinite dimensional one. So the key point here, an outcome that we can also be thinking. I mean, in parallel, let's say, a different set of reasoning here. We think of ourselves high-spin gravity as non-commutative geometric dynamics or symplectic geometric dynamics. Okay, there's also an outcome here that I cannot personally find very pleasing. Is that guided by applying a variation principle to an action, we can think of essentially matter. Okay, the matter is like Einstein's theory of geometric dynamics. I'm using the same analogy. So matter are quantum states, okay, or operators, or zero forms. Okay, so they move following evolution equations in the presence of connections with curvature, but the curvature is deformed by the quantum state. If something is essentially quadratic, okay, the quantum state. So it's very similar to Einstein's theory where curvature is stress energy, and the motion of a matter on a manifold follows, say, geodesics, right? There's a very similar picture here. We have a symplectic geometry. It's deformed by the presence of quote-unquote matter or quantum states on that manifold. And the way the quantum states evolve is depending on, of course, on the symplectic geometry, including Hamiltonians. And everything is an interaction here. Okay? So, of course, this gives you an idea that maybe this gives a way to extend to the linearized version of this ordinary quantum mechanics. Of course. So when it will be natural non-linear deformation of quantum mechanics. Good. So that's one key point I would try to stress here, or I mean, not pass it through it. And the second point is that massless particle states. I mean, when we read what is a particle state after all, or you have a vacuum projector, right, in quantum field theory, and then we act on it from left and right with creation annihilation operators. So that structure of QFT, the vacuum projector, is now a composite operator. Okay. The vacuum becomes a composite operator built from non-commutative coordinates, which are the creation annihilation operators, arising from deformation quantization of a Weyl 04 module. So these are the two kind of, I would say, key points here. Okay. This is the first quantized. This is classical high-spin gravity, maybe I should say. Okay. So as a classical theory, it has to do with the moduli space of the theory that describes these non-commutative geometries, and there is this interplay between curvature and quantum states or matter. The second one has to do with the second quantized theory. Good. I'm going to skip this slide, but so there are some topics that I find fascinating where all these intersect. One has to do with the TFT functors, okay? So in TFT, one usually has finite dimensional Hilbert spaces, but here they become infinite dimensional. And that has to do with the fact that we are putting defects on the manifolds, and on those defects, we allocate the states together with something called partial actions, or sometimes it's also referred to as weak actions or boundary actions that provide on-shell actions. So when you trace the identity, you don't trace an identity operator, you trace the partial action, which provides a weight, or you can think of it as a Boltzmann-like factor, thereby overcoming the problem with applying TFT to QFT. Okay? This is nothing new, of course. I mean, it's known for a long time, but it's just to keep in mind that one can apply TFT to even ordinary quantum mechanics. We have infinite dimensional Hilbert spaces in the presence of partial actions. Okay. Non-commutative field theory, of course, as a non-linear quantum evolution equations, also something that I find interesting, pleasing somehow. And then, and I'm not going to here, but the resolution of classical singularities in gravity and Yang-Mills theory. Because gravity and Yang-Mills theory, once they're embedded in non-commutative geometries, many singularities that you think of as hard, nasty singularities, once they become embedded in a non-commutative geometry, they are simply due to essentially artifacts due to symbol calculus. Okay? I'm not going to mention this anymore, but I find it also very interesting. And finally, I will come to that. Something we refer to as fractional spin gravity, and using quantum group values. So I will try to flash it towards then. High spin gravity has all the integer spins in it. But by playing with equations, by choosing different embeddings of the Lorentz group, you can achieve fraction spin, infinite dimensional fraction spin representations in the theory. It is at the expense, when you go beyond three-dimensional, beyond ADS3, let's say, it's at the expense of losing the isometry group. Okay, so if you're in 4 dimensions, you have really 4-dimensional domain wall. Okay, but there are fraction spins in there, and this sits as different branches of one and the same master equation. One branch is Vasiliev's theory, which we can call the bulk higher spin gravity, and another branch is a fraction spin gravity, which is conformal and lives in 3D. Good. So these areas, these topics are kind of joined here in my talk. Okay. So the first part, so I will discuss 2 different ways to approach the relativistic particle. Either you can think of it as usual, there are vanishing Hamiltonians, p squared is 0. Now the target space is space-time. Okay? Or people like to also think of systems with non-vanishing Hamiltonians, like say an H atom. Okay. Now instead, it's better to think of the target space as a full symplectic manifold, and you add this T star G extension. Okay? Thereby you can compensate. You don't need the Hamiltonian to vanish anymore. It's still a reparameterization of Lorentz system. So I will start with this. And then apply to the conformal particle to obtain the type A model. So here I'm intersecting with work of Jacques-Bars, of Vasiliev, and also of several unit orders, Alkaliev, Becker, Grigoriev, and Skvortsov. Their formulation of the type A model sits as a branch in this theory. Okay. And it's important here there's an additional on the world volume already, world line, in addition to SP2, which is part of the conformal particle gauge group, SP2 is a gauge symmetry of this type with the vanishing Hamiltonians. There's also GL1 gauge. So GL1 seems very, it simply means that there is a set of ghosts generating a graded Mach-2 algebra. That gives this Probienchen-Simon structure. And by deforming the Beer's operator, we get this FCS model. Then I will comment a bit about discretized strings, partons, and how the symplectic bosons arise, starting from string theory, making contact with Gabriel and Gopal-Kumar's recent work. So here one can see, for example, by using these ingredients, I didn't stress it enough maybe, but so we can construct it. For example, a simple example is the n equal to 6 theory in ADS4, okay, which has to do with type 2A on CP3. So that theory now sits as a critical W string instead. And to achieve criticality, we have to join these ideas. We have to have, or these ingredients, we have to have the GL1 gauging, and also, as I mentioned before, this fibered non-commutative geometry, the Z coordinates, if you want to see this here. Okay, good. And then part 2 is second quantization. Good. I'm looking here at my clock. So let's start with absolutely most basic thing we have. I mean, the one-dimensional classical mechanics. I have a particle mass M, potential V. Of course, written like this is not diffeomorphic invariant on the Verl line. Okay. So one way of restoring that is with Einbein, but let's do it like this instead. Let's simply introduce a Newtonian absolute time T. Okay. And insert its derivative with respect to Verl line parameter tau in strategic positions. So now the action is, of course, reparameterization invariant. You can check that the equation of motion by varying T is simply the conservation of energy. Okay? And you could, of course, gauge fix. You can put T equal to tau and go back to this action, right? If you go to the Hamiltonian form, then there is a momentum S for T. So we have PDX plus STT. And then there is a Lagrange multiplier. But this is not an Einbein now. Okay? This is a different type of gauge field. And it multiplies the constraint where the Hamiltonian doesn't have to vanish, but the Hamiltonian is simply set equal to, in this case, normalized to minus S. So the momentum of this absolute time S is equal to the Hamiltonian, minus the Hamiltonian. So now there's no need for the Hamiltonian to vanish, even though the system is parameterization invariant. Of course, another path one could take here is to start, we go here, we go exactly here, but then we can say, this looks like a, perturbative expansion of square root t dot square minus x dot square, right? I mean, and you go to the relativistic part in xt space, Minkowski space, of course, x and t. But I'm not doing that here. Instead, I'm keeping t at the side, okay, as an evolution parameter, and I keep my symplectic manifold as R2 in this case. And here's the Hamiltonian. So now I have a Hamiltonian action on the usual symplectic manifold, okay, cross t star of a group, okay. So the group now is just R, okay, time evolution. So this we can generalize to a gauge model of the symplectic manifold M on which a group acts, okay. So this means that the group acts in a friendly way, okay, on M. So there's a symplectic structure here, and hence every group element, every generator of the group counts with the Hamiltonian function. I call them H here, and here's now the action, okay. It's just a straightforward generalization of what I've written here, okay. I have to put a bit of indices. And indeed, if it's a non-abelian group, the Maurer-Cartan form appears here, okay. I can see something here on my screen. I'm not sure. I don't want to block what you see. Okay. Good. So here is a good generalization. And we can, of course, introduce generators. I mean, here, these are just the generators, abstract generators in the algebra. Good. So the constraints here, so varying A, of course, I have constraint S plus omega mu R. So this HR, again, are functions on M, right? So they're functions of the symplectic coordinates on M, right? So here I'm using the Poisson bracket to compute, to close this algebra. So now these are abelian constraints, okay, it's all fine. One can do constraint analysis. So what we could try to do now, I mean, it's written in maybe, here you don't see really the group structure, but we can actually write the explicit terms of the group element G. We'll do that later, it simplifies matters. So if you define a Lie algebra value connection, the Lagrange multiplier is naturally the dual of the Lie algebra, okay? And here we use the left invariant vector fields, okay, to do this conversion, the inverse of the Maurer-Cartan form. Omega here, right? It has it's an invertible matrix. Good. So now we can write it like this. So here we have this piece here. I can think of it as a covariantized version of these kinetic terms, right? These are P-symplectic forms. There will be essentially P, coordinate-free version of P dq or P dx, and this is now covariantized today. And here I covariantized the derivative of the group with the right connection, okay, A. At this stage, one can apply A to Z formalism. I can extend all of these guys to superfields, okay. So for example, A is now will be a superfield of degree 1. So there will be a zero form of ghost number 1, which will be the ghost, and there will be one form of ghost number 0, which is the old A. Okay? But the same thing with G and the coordinates on M, all of them become superfields. Okay, we can add also, it's natural here to add a variable, a dual element of total degree -1. So here you have a zero form of ghost number -1, which will be the conjugate variable of the ghost here. And there is one form of ghost number 0. Of ghost number -2. And then one can just add an extra term to the action. This way it's more democratic because all fields have now kinetic terms. Also A is a kinetic term, right? So gamma is the Lagrange, the momentum of A, and it makes sense as a superfield. Okay? Clearly, you cannot have a -1 form, but you can have a total degree -1 superfield. Good. So this action here is based on Masterfield equation. Here one have to use, I think there have been lectures in this conference by Cartan, for example, how to induce the BV bracket from the symplectic bracket on target space using evaluation maps, etc. And in the cohomology of the resulting BRST operator, the equations of motion, these are not really the images of this, for example, the first term here is little s applied to phi a, etc. I think those who are experts find this trivial. Those who are not experts, I encourage you to read more about this. But these equations here, which are Masterfield equations or superfield equations, form a Cartan into the system. Okay? I can check. For example, if you want to hit this equation here, for example, with D, you get curvature acting on S star, but curvature is 0. So that's good. Here, for example, you get curvature is 0, ds is 0. You get d of h dual. But this element here is t dual r, hr. You can differentiate using chain rule and use this equation and closure, etc. Then you find that this is also compatible, okay, with integrability. This is an integrable system. And of course, as such, you could actually have started thinking of putting this theory in some arbitrary odd dimension, for example. Good. Here we have been forced into use also the poisson-friendly vector fields. Good. So far, what do we have? We have essentially a symplectic manifold. A group acts on it with Hamiltonians, and Hamiltonians don't have to vanish. Okay, and in that sense, if the group G is, for example, sp4 and the manifold M is R4, I could call this a relativistic particle. I mean, it's a particle on whose state space sp4 acts. Okay, and as we all know, sp4 is the isomorphic group of ADS4. And this is in fact a conformal particle, Dirac. Okay, so this is a relativistic particle. It's just that the target space is not the usual space-time. It's rather a symplectic manifold on which a group G acts in non-vanishing Hamiltonians. Good.
Can I ask you? Can you please specify what Cartan integrable system is? So I'm not sure with terminology.
So there are 4 variables here. Phi alpha, which is the degree 0 field. Okay, I should have said. There is G, it's a group element. Again, it has total degree 0. There is A, which are degree 1 fields, and then there is S, okay, which is degree 0, and gamma, which is degree -1. So it's a bunch of form fields. Okay, you can all write it down in explicit components if you want. And
what's integrable in this?
Yeah, the RAM differential D squares to 0. For example, if I hit this with D, this goes away, and I can distribute here using Leibniz rule, and then I back substitute the constraints, and then I want to get identities here. And it's called an anomaly free Cartan into the system. Okay? Or it's more practical to work with covariant differentiation, of course. Okay? You can check that these equations here, there's no obstruction to integrate the system.
It's compatibilities. Compatibility.
Of course, there has a lot of consequences. I mean, you can actually integrate.
It's okay. Just compatibility holds. Okay. The system is consistent.
Yeah. Yes. Good. So now, but of course, we can introduce a second. We can use more groups here. We can introduce a second group. I will call it G twiddle. Here, the Hamiltonians will vanish. Okay, that acts on this whole package here. Okay? So these Hamiltonians, which will vanish, are functions on M cross G to R. Okay. So they can also act on G here. So it's not necessary that they commute. This is not a how dual pair yet. At some stage, we can do that, of course. I can kind of restrict G here to a group that actually commutes to G tilde, but at this level, it doesn't have to. Okay? Then I can assume as background field equations, the following set of equations, that the RAM differential on G on H twiddle, because H is a function of G, right? I can differentiate it. Plus the Cartan form, okay, and it is, I write this H dual on omega, meaning HR omega R, okay. So these are one forms, Cartan forms, these are the Hamiltonians. And I compute this bracket here in M, because indeed H tilde is also a function of M, so this can be computed. So I impose this constraint here. You can put like an exclamation mark. These are not variational, these equations, they're just background equations, okay. They will become variational later on. And then that they form an algebra, that's still important. Okay, it has to be a group. Okay, good. Then you can extend the model a bit. You can add an extra set of connections, call them H tilde, for acting with these Hamiltonians. So you have an extended covariant derivative here of the matrix system. you still have the T star G extension, but there is no T star G tilde extension. Okay, so these Hamiltonians, so the Hamiltonians of G tilde must vanish on check. Okay, of course you can. It's a free word, so you can just put the G to. You can drop him, right? Taking trivial. Okay, and then this is just the usual. For example, SP2 constraints or Virasoro constraints of the string, etc. These are the vanishing Hamiltonians, and this is the non-vanishing Hamiltonians. Okay. Good. An observable now would be a function, okay, from this space here to R. Okay. I mean, you might want to put here T star of G. I actually asked myself, why don't I put T star of G here? But I took the function M cross T star. And it should satisfy, this comes from the BRST analysis of the system, that an observable must satisfy these constraints. So you see now that observables, they satisfy a Cartan integral system up here, a Cartan integral equation up on G, okay? So when you add T star of G to the target space of the particle, you get on that factor of target space an unfolded equation or a Cartan integral system here. So there are two Cartan integral systems. One is the one down on the Verl line here. This D here is on the Verl line. And then I have another one up in target space here, okay? And you also had these equations, remember? Okay, so this equation here for B, observable, which you can think of as a linearized fluctuation if you want. And these background equations here, we would like to unify these equations. I would like to put them in one master equation, okay? So I have a background again. I mean, the particle moved in the background. I put an observable, a function on this target space. And I want to think of these two bits and pieces as two, I want to think of B as a linearization around this background. And there should be in one non-linear set of equations governing it all, okay? So how to do that? Of course, there's something in the one game in town. Let's simply deform the BRST operator, okay? So we have the original BRST operator on T star of G. So I didn't say, that's why I dropped I took B here to be functional of only G, because the dependence on the fibers will go away on the BRST homology. And then there's a perturbation, X, okay, which will be our master field, the Fefferman-Simon master field. The BRST operator has this form. Remember, these were abelian constraints, okay? So, so this is the BRST operator. I will put the extra piece here from the abelian constraint that was the omega h in the background expectation value for X. Okay? So,
sorry, Perry.
Hello? Yes, Xavier? Halfway. Hello? Have I contact? Hello, hello. I'm the audience.
Can you hear me?
Yes, I hear you, Xavier.
Okay. You just asked me to remind you when we cross the middle. So,
Good. So I will
well, just for your information. A few minutes ago, I guess.
Good. So I'm deforming this BRST operator, this squares to 0. Okay. And then, of course, we get this equation, the adjoint action of this operator on X plus X squared is 0. And then I can show that if you start with functions of S and T on T star of G and B and C, you can compute the cohomology here, but it's the same thing as computing the drum cohomology on forms only on G. By forms on G, I mean functions where I deleted the B dependence and I deleted the S dependence. Okay, so we can do that reduction and restrict X here to a form in omega of G. Okay, and then it has to be function on M, and then comes the ghosts from GT. And then the original BRST-Vilkovisky condition becomes this equation here. Okay. So again, I'm using the fact that the cohomology of this operator here in the set of functions of all the variables coming from T star of D is equivalent or isomorphic at the linearized level to this cohomology. Okay? And this cohomology is a sub-algebra, algebra. So I can take X here and multiply it with itself and it stays this algebra. Good. So, that's the first step. And then the second step is to take this G tilde to contain this GL1 factor and something else. Okay? And then from GL1, I mean, there's this gauge field A tilde, there's a GL1 gauge field upstairs. It will provide ghosts, okay? I call them here F and F tilde, okay? So F is degree 1, F tilde is degree -1, and I can then expand X in the complete set of bases for this mat2, okay? This is the 3-graded mat2, okay? So this gives a natural set of fields of degree 1 here, A and A tilde. This field B has degree 0, and this field B tilde has degree 2, it's a 2 form. Okay, so this B here, of course, will be identified when you linearize with the B field upstairs with observable. And this in A, I will put the wave for omega. And B tilde is an additional bonus. Okay, it's a dynamical 2 form. So we get the Frobenius-Simon's equations of motion. Okay, on G. Okay, so notice here that the curvature now here is deformed by B tilde. So B is 0 form times the 2 form. So this makes sense. And thanks to these two equations, this is an integral system. Okay? So this is a Cartan integral system. I mean, it's clear, of course, from the way it was constructed, but written out like this, it looks maybe more messy. But indeed, these equations have been used. I mean, this is essentially, you can think of this as Chern-Simon plus matter and so on and so forth. So they have appeared in various different settings. And indeed, we also use them to embed Vasiljev's theory in an dimension Simon theory with an action. And then I can give a background wave, okay, to X. So there was already this little Q here, my kind of proto-BRT operator, but then I'm adding a wave to X, okay? Then I get the new wave for Q, kind of shifted a bit, where I threw in this piece here that contains the Hamiltonians, and also I can also, of course, have a BST operator for G tilde prime, and I can also throw in here 2 forms on G, okay? So this is a closed and central form on G. Okay? So these are interesting guys. We haven't studied them that much, but roughly speaking, it's like putting conical defects inside space-time. Space-time is here. And just to say, roughly speaking, what happens, so if we switch on the linearized B, of course, via this IG, it will backtrack by BIG to A, okay? So the Hamiltonians that sit in here are now dynamical. So they will start depending, the Hamiltonian that you want to evolve the system with depends on the system that you try to evolve, okay? So this is this geometric dynamics program. Good, but still we haven't seen any deformation of the symplectic structure on M, okay? So how do we do that? So the idea here is to extend the differential Poisson structure, this Poisson structure on M to differential Poisson structure, okay? So you want to deform forms, or in particular symplectic structure on M. And to do that, one has to introduce a connection. You can use a compatible connection in the symplectic case. So this Poisson bracket here is for forms. So rho and sigma are forms on M. And one can define a Poisson bracket like this. If then this R, this curvature here satisfies certain integrability conditions, then this is a consistent bracket. It's called a differential Poisson structure. And there's a sigma model for that, okay, that we can gauge, okay. And the upshot here is that when you quantize this sigma, you see that the usual eta d phi plus eta pi. So when we quantize this, you get back the original. In the symplectic case, this is just, of course, if you integrate out the eta, so just go back to the boundary, and you have the original particle on M. And then because here, this ties, of course, the work of Cartan, Felder, and Kontsevich, and the star product. But there are also fermions here now, okay, in this curvature term. So roughly speaking, when you contract the thetas with chi's, you produce this extra piece here in the semi-classical limit. Good. So this is in 2 dimensions. There are defects, we call them boundaries if you want, where the etas and chi's vanish. On these defects, there is BRT cohomology. Okay, there the functions of phi and theta here. Okay, so functions of phi and theta, what is that? these are just, you can think of them as forms, right? You expand in theta and symmetric and the coefficients of phi. So these are differential forms. There is a star product for this system, and there is a de Rham differential also. Okay? So there is a natural bundle structure appearing, okay? Because they have the zero modes, the constant modes, the constant in phi and also constant in theta. Constant modes form fibers. Okay? They're essentially just a center of mass. Okay? And there is a base here also. And how does the base arise? It arises via logarithmic modes. So this is, one have to remember, it's a two-dimensional sigma model. So if you have a boundary, you could have you can have a cusp on the boundary, or you can think of it like this is an open string. So that two boundaries moving at a distance from each other. If the distance between the two boundaries is z, it appears as a logarithmic mode in these two-dimensional fields. This, of course, one have to do a lot of computations, but in the full string field theory, there is a zero mode and a logarithmic mode. That's special. They form this kind of bundle structure. Okay? And there is a super trace operation. We can integrate out y and z. Okay, so you can trace over this total manifold. That becomes a super trace because you're integrating forms, right? So it's naturally graded unsymmetric. So the two supersymmetries, the BSD transformations, which gives the de Rham differential. Okay, so these I didn't mention here, but that's one of the reasons one puts these couplings here, right? To have this supersymmetry. If it wasn't for this term here, you wouldn't have this symmetry here. Okay? So that gives rise to the de Rham differential on the total boundary space. So here you can expand again phi. You can write phi alpha as y plus log, the logarithmic piece, z plus oscillate, okay, and decompose. Then you get de Rham differential acting on y and on z. Okay. But then there are also other symmetries which are have Gauss number -1. So delta phi is 0, delta theta is a boson. Okay, it's a vertical vector field sitting here. So if these are symmetries, one have to give conditions on the curvature for that. Then you have fermionic zero modes. Okay, so the fermionic zero modes induces a volume form. Okay, on a fiber volume form or gamma in the forms on m hat. So this is a form. It's a form on m hat, but it spans the fibers. Okay, it has to be closed in the center. Good. So we have that ingredient. So gamma is a form, has the same rank or degree as m, and is closed in the center. Okay? So that means that one can go to horizontal algebra. Okay? You can factor out the kernel of left multiplication by gamma. If it's left or right, doesn't matter because it's center. Okay? But so you identify a form with itself plus any tau that's annihilated by multiplication by gamma. In the operator algebra. That's an equivalence class in here, okay? And this algebra, so notice usually sometimes when use the word horizontal form, these horizontal forms can be zero forms on the fiber, okay? They can depend on the fiber coordinates, but there cannot be one forms on the fiber, okay? Because if you have one form on the fiber, you're in the kernel, it can be factored out. So this is, it doesn't exactly agree. I mean, that is another definition of horizontal, namely that your forms invariant on the linear derivatives long fibers. Okay, I'm not using that one. This is just essentially invariant on the inner derivatives long fibers. So here, this is a DGA. Okay, there's a differential defined in natural sense on the equivalence classes. This is a product, and this is a super trace. Good. So here again, so the master fields or the string field, if you want, we live in this horizontal algebra. Okay, so hence I can differentiate along the base. But I can expand it in zero forms along the fiber. We can play the same game again. We have just more pieces in our action. I had the original piece. I have a differential that's nilpotent on m hat. Okay. So it looks a bit funny maybe, but I'm using now this e and e tilde. So you see here, to put the differential on this symplectic geometry here, I need this GL1. Okay. This now squares to 0. Okay. Because when I written it here, when you square this s here, s squared is essentially the symplectic form on m hat, but I can subtract it off with this piece here. And it all has degree 1, right? This has degree 1 already. This degree -1, +1, +1. That becomes 1 also. Good. So the superconnection, which is the perturbation of this stuff, it's a horizontal form. It's a form on G already, the extra ghosts, and then I threw in also Klein operators. Okay. And I get the following equation. Now here is a subtlety we are trying to understand, but you get this extra piece here. Now it turns out that when you apply this to later on to type A model Vasiliev branch, you can remove this piece by field definition, but it really sits here. Okay, this is the volume, the symplectic forms or an M times this essential identity operator. Okay? So it has to be there in order to come from the BRST operator. But when you go to Vasiliev branch later on, it's removable. Okay, so you could actually delete it. I could put the parameter here. It's not fixed by anything. Okay. So someone can have a good idea why you should actually throw it away. Maybe you should go back to the beginning, make the whole thing anomalous, and then it's disappears. I've been thinking about that, but okay, this is kind of inessential for now. You can again switch on the background. Just that now these two form here can have conical singularities not just on G but also on M hat. Okay, this non-commutative fiber space. Okay, and two forms. They are close and central, naturally codimension two conical singularities. That's the simplest way to achieve such guys, I should have said. Okay. And in particular, in the Vasiliev system, I think we all know there's this peculiar DC square kappa that comes from a conical singularity here, okay, combined with Klein operators. So here there's a huge moduli space we're exploring, but in particular, it contains the usual Vasiliev branch. And we have this usual, again, the statement of symplectic geometric dynamics. Okay. Now B deforms not just the G Hamiltonians, but also the symplectic geometry on M. So here again, to refer to computations, but so there is essentially the fiber and base, but when you switch on B, you deform the base symplectic structure and the fiber symplectic structure together. Okay. So the type A model will be simply achieved here by taking M to be R to N, SP to N rotates it in a faithful way, and an SP2 from outside. Okay. This we can call the non-commutative ambient twistor space. Okay. But notice that there is a fiber base also here, the Z coordinates, okay, and the fiber. When we choose SP2 algebra, I have to break SP2N to SOP, Q. P plus Q is Z. So this is the isometric group. And there's yet another breaking by this central closed element here on the base. Okay, that singles out the Lorentz group. So, so these algebras here, or this space of functions, in the end is broken down to Lorentz tensors by choosing waves in two steps. Okay. First isometric tensors, then Lorentz tensors. So here I just given the Vasiliev branch. So now we can land on Vasiliev equations. It sits inside the system. It's important here that we have these SP2 ghosts. Okay. So now we can factor out, I mean, this system here, so I should maybe stress. So this is W here, as you can see, that functions of SP2 ghosts also. So if you expand it out, there are only a finite number of ghosts. There are 6, right? There are 3 B's and 3 C's in here. So it's a finite number of it. You get a huge number of equations, of course, but it's integrable now. And now you can factor out SP2 while maintaining Cartan integrability beyond linear level. So the works done, there was original work by Vasiliev, later by myself and by others here in the audience. This factoring out of SP2 by shift symmetry is not entirely innocent. Okay, you have to put the ghosts here. It's kind of obvious in a way. And when you do that, there will be back reactions actually. Okay. So higher up beyond the linearized level, those shift. When you factor out shift symmetries, those fields have their own Cartan integral equations of motion. Okay, and there will be a back reaction from that. But it's all fitting into this big system here. Of course, the notation is a bit fallacious maybe, but these are really forms cross fields with ghost number. And the total degree, again, is 1. Okay. So in some sense, little hat here is a bigger field than usual. Good. So this is the fully nonlinear type A model. We claim at least that it really has to be done this way. It cannot be done without the ghosts. Okay. We can reduce, I can put B to 0. I still have to keep the ghosts, however. And then we get the nonlinear completion of the model of Grigoriev and company. Okay. So here there's no Weil zero form. It's all all the juice comes from the sp2 generators in this model, but it still has to be, well, the equation takes this form. Just put b to 0, okay? Just this equation. So this equation here, when you expand it out over ghost, you will also get the commutation rules for sp2 generators, because there is a nilpotent BRST operator condition. There's a zero form constraint, in other words, hidden in this equation. Okay. So when we write, I should maybe stress again, when I write this equation here, this term is at least form degree 1, right? So you can project this down to form degree 0. Then only this term together must vanish. You get zero form constraints sitting here. Good. I will skip this. Just to say that one can also do Cartan-Weil conformally covariant type A model. It's almost by stroke of a pen. You simply play with null vectors in the target space. Then you lose. Okay, you go to ADS n minus 3. Okay. You change, in other words, G tilde. G tilde, instead of being sp2, it becomes sp(h)(2). Okay. I'm running out of time, but let me just very quickly. So these conformal particles, they arise as solitons in the number Goto actions. If you have a string in ADS and it starts rotating, there will be portions of the string, this red blob here. So this is the string, this black line, but it will reach a cusp, okay? And if you compute the energy and the spin of this, of course, the whole string has a total energy, and total spin is an integral along the string, but the contribution from this bullet here behaves as a conformal particle, approximately. Okay? There's a small anomalous correction. Okay? So if you have many cusps on a rotating string, T of them, let's say, there will be, you will have states in the semi-classical description of the string that forms these linear trajectories in a mass spin table. Okay. Clearly, when you have very short strings down here, then you can approximate everything with flat space. Then you have Regge behavior. Okay. M squared is spin, but so M is square root of spin. But they will straighten out in a crossover region determined by the tension, okay, and become these long straight lines. So here, in particular, you have to have at least two, okay, cusp. We cannot just have one cusp. It has to be two. Then you have the Gupser-Klebanov long string. This yellow line here, sorry, green line, that's the high spin gravity part of the string then in ADS. And down here, on the same line, which has crossed over, we have ordinary gravity. Okay? So this I think of, I really think this is the Hagedorn crossover, okay? You start with strings, you think you're in flat space, but you really sit inside an ADS space as a form of infrared regulator. And at some point, you will reach this spectrum, right? Doesn't matter how big L is, okay? For any L, there is always the infinite, I mean, you have a finite number of states with Regge behavior, finite. For any little L, doesn't matter how big L is. And then you have the rest infinite part of the spectrum are forming this tensionless branch here. So what do? The Virasoro strings, we put them on T star Rn. So I embed ADS as a time glass, okay, using second class constraints. And then we have the usual first class Virasoro constraints. So this is just Virasoro action in ADS, okay? ADS embedded as a time glass. Okay? So the combination here of first and second class constraints is kind of ugly, but that's what it is. You have two Virasoro algebras, yes, left and right movers. But what we do now, those proposals with Enquistment, is that, okay, let's take tension to 0. We drop this term, but we also take L to 0 at the same time, because the usual argument would be, but wait a minute, isn't everything just a function of TL squared? Okay, well, it's kind of true that the Virasoro string only depends on TL squared, because I could just rescale variables here, right? If I want to take a limit, that's a separate limit, to take them separately to 0. You could see this if you discretize the string. I'm not going to go through it here, but then there's a third parameter here in terms of which the lattice spacing, if you want. So you should take both these to 0. Then something nice happens. These three constraints here combine into an sp2 algebra, right? And you're left with one Virasoro constraint here. Okay? This is a carrier Virasoro algebra in an sp2. Well, I mean, not so fast because X is kind of conformal weight 0. This is conformal weight 1. This constraint is conformal weight 2. But one can twist the stress tensor. Okay? So you can subtract from this stress tensor, you can linearly recombine the constraints. I can subtract the derivative of this guy. then you get this twisted stress tensor. With respect to him, both x and p have the same conformal weight half. Okay? And the total central charge is now minus n of the Cartan-Vilkovisky algebra. And then there is a central extension of sp2 also going on here. So it's not particularly critical at this level, right? But the idea now is to add on constraints here fixed by criticality. So we also have some kinematics here. If we symplectic bosons, as they're called, goes back to work of Senechal and others, they observed long ago that there is a very nice feature of spectral flow. So spectral flow is a way to generate essentially from the identity operator or the Navier-Schwarz vacuum. You can generate the whole spectrum of the theory. It's an integrable system in that sense. Also, of course, by Gabriel work in the 90s on spectral flow. So one can use those works to show that when you flow n p times, there will be zero modes in the wedge. Okay, this has been also recently stressed by Gabriel and Gopal-Kumar. And these zero modes are now represented unitarily on a flowed. This is the flowed Navier-Schwarz vacuum, okay, in singleton representations, in multi-singleton representations. So this was also done around 15 years ago with Enquist and myself. We also in the context of tensionless or discretized strings. So the conformal particle, quote unquote, reincarnates inside this symplectic boson theory. Okay, a little bit funny. I mean, you start from a string. Okay, in some sense, you may say that on the string you have the cusps, right? Here there are solitons, and there can be many solitons. A bit chaotic. I mean, you can have a lot of cusps, right? Each cusp is a conformal particle. Then you take this limit, and voila, here they come again, but from spectral flow, the same kinematic degrees of freedom. But there is a lot of chunk, okay? Outside this wedge, there's an enormous number of unphysical states. So how get rid of them, okay? And this ties to this criticality here, okay? So we would like to have a, I mean, in that sense, double symmetries are actually kind of good because double symmetries have this effect of washing away essentially all fluctuations except those in the wedge. So this is a suggestion, okay? I don't have time, but the idea we had with Enquist was that, well, let's just tag on, you know, you start seeing the pattern, right? There is a triplet here. Hello?
Yeah, sorry, just to remind you, so we started a bit after, but you really have just few minutes, right? Few minutes left. Huh? Really few.
Here you have a singlet spin 2, so you can just extend this double algebra. You have conformal spin 3, a triplet again, and so on and so forth. Okay, we call it WSP2 plus infinity. This says if you use zeta function regularization, you get Gauss central charge 2, okay, and 0 SP2 anomaly. Okay, so there are two problems now: how to make it critical, and also the zero modes. Okay, so the zero modes we deal with by putting the Kyle bosons on S1 cross S1, the torus. It's nicer. I mean, we want to do deformation quantization. These particles should move on the circle. Okay, that means that there is only one zero mode for each spin H Gauss system. In particular, we can call it B0, C0. Okay. Whereas if you would be on a sphere, you would have a, you know, grows linearly with the spin, etc. Here it's much nicer to be on the torus, and it fits this idea of deformation quantization. Criticality, here the idea is a bit more brutal, but I mean, essentially, we to achieve a critical string, you're free to do the following. We want to restore nilpotency of the BRST operator, okay, and preserve the target space symmetries. Okay? And we can do that by adding an anomalous sector that simply factors out on the restored homology. Okay? It's a bit like how the Liouville field appears in string theory, which is not critical. Okay? You say, well, I mean, just add an extra degree of freedom, such a homology, and then you can factor out that degrees of freedom. You get an extra transverse degree of freedom, gauge condition. So here the anomalous sector we propose are an extra set of symplectic bosons. These are the Z variables, but they appear in a completely different way now from before. And a bunch of real fermions. So again, on the differential Poisson sigma model, only these two guys, the logarithmic mode and the theta coordinate. But now we also have this guy here. Okay, these are real fermions. Okay, so that means that there's a contraction between this is a Clifford algebra. Okay, now that this system here has central charge equal to minus that of the Y system, original symplectic bosons. Okay, because there's you can see it here. I mean, well, if I put Z and Y system has the same center charge as theta theta star because of the indices. Okay. So this cancels the C anomaly. And the SP2 central anomaly here is the same, this minus sign here. Okay. So that means that, okay, good. And then I should add this GL1 ghosts. So this algebra here is too short. I should put here with H is 0 a singlet also, which is not really gauging a current, not a it's just an extra set of fields, but you can call them spin 0 ghosts if you want. That has C is -2, okay, and no SP2 anomaly. If you sum everything up now, it's critical, the total charges, okay. So then, of course, the proposal is, we go to P is ±1 sector, the Virasoro plus infinity, that wipes off everything except the wedge, okay. Then I can just play the game I had before, essentially, build the BRST operator. X is here as a function of these modes, and so on and so forth. Okay. Now, we are relying on one detail here, which I haven't proven yet. Someone is an expert, that I can also truncate, I can, on the cohomology, I can factor out this theta star alpha. Okay, didn't have it before. Okay, but now I have it. But I can still use exactly the same form for this QM hat. Okay, that squares to 0. Okay, so this is something I'd like to show. Good. I'm out of time. The second part here, I will do it in 1 minute. Second.
Well, 1 minute maybe for the second part.
How many seconds?
Well, 55 seconds. Is it okay for part 2?
So the classical solution space of these theories have something called Weil zero form modules, and they have a Kähler structure, the positive and negative frequencies, and you can just abstractly put the Kähler structure on that manifold. Okay. Then to quantize, the idea is to use this T star G extension of the FCS model. So let me give you that. Okay, so here's this field B is just an operator. If you take it that has positive and negative frequencies, okay, with the Kähler structure. I mean, it's just the trivial one. It's just, Z, the complex Z and Z bar. Okay, so that's the one we want to quantize. Okay, so the idea is to think of a defect, which is just a Weyl line, okay, as a boundary of a one high dimensional manifold with sigma model maps of AKZ type. Okay. And I can maybe go to the point. So the total action will be a bulk part plus a boundary part. The bulk part is this standard Hamiltonian action with this symplectic form. But take the sum, right? S bracket S, S total bracket S total 0 means that S plus 2SK should match. And then we can allow an anomalous potential in U as long as there is the boundary action is anomalous. Okay. So how do we achieve this? We start from this partial action. So I have the original FCS connection. I threw in a friend on the right, okay, and add the T star G extension. So this is now the partial action, the boundary. You can check that this is anomalous, okay? And here okay. There's also one extra bonus here that we also duality extends the 0 forms in B and B tilde.
We are
so
about -2 minutes per.
-2 minutes. But there's an extra large gauge symmetry that takes care of that. Okay? So here I have the classical anomaly. And then I just add this bulk action. This is kind of trivial. You have essentially the FCS action here, plus the classical anomaly, the right part, and then this group sector. And then we can check that the 0 form constraints imposed here. I will stop here. But the 0 form constraint, because these are anomalous variables. You didn't have time to see it, but when you want to cancel anomaly, you have to put Y to 0. So what we do here, we first commute with Y and these operators on states, and then we put to 0 Y. Okay. And then you can show that you can solve these 0 form constraints at the quantum level. Okay. So what has happened here now is that the Y 0 form model has been quantized. Okay. I have non-trivial operators. There's a cohomology from these constraints. And when you build in the operator algebra, you can build vacuum projectors, and from them you produce massless particle states. Okay. There is this, okay. I have to stop here. I have to go at least something that looks decent for a summary. I have a summary here. Okay. Then I will stop and ask for questions. Okay. Good. Sorry about that. I didn't have time to go through the second quantization very well. Okay. Thanks all for your attention and for the questions that I missed in the questions, but
thank you, Per. So let's thank Per. Are there some questions? Can you hear us? Yes. Huh? So in terms of applications, Per, to the same old problem of variational principle, this provides new insight. It's part of this program, I guess, right?
yes, I mean first we have this Frobenian-Simon theory so far in high dimensions, let's say 9 or something. But when you try to quantize, if you take that action at face value, you don't it doesn't deform, it doesn't quantize the boundary states. Okay. So what we've done here is to push the dimension down to 2, the 2-dimensional bulk. Okay. A flash action up there. So now there is a natural symplectic structure in that action. There are p-square terms. This is like a BF theory, okay, in 2 dimensions. The p-square terms that puts holomorphic symplectic structures that contracts B with B tilde. So in B tilde there's a 0 form. That's, okay. And then by this extra large gauge symmetry, we can identify. Okay, so at the end of the day, we end up with a Kähler structure on the Weil 0 form module in this model. Okay. But we are forced to sacrifice something. Wait a minute, we're on the disk, the boundaries of our lines, what's going on here? But then there's of G inside the target space. So the original, ADS4 sits up there now in the target space of this model. So I was trying to explain in the beginning. So that's, we have to play anomalies. It's a bit painful there. A lot of technical things is in the slides. I mean, several things we don't understand yet, okay? But it looks promising, okay?
Thank you.
Quantized massless particle, particle creation annihilation operators. That is what we want, okay? In a very particular model. Then, of course, I mentioned here, you can we apply this to GR or Young-Mills theory? Very good questions. Many things to do here, but you want to